Hello everybody. Thank you for inviting us to the OpenNebulaCon2022. My name is Daniel Dehéna and I'm member of the Pôle de compétences logiciels libres in the French National Education Ministry. We can translate it as the Libre Software team. Historically, we built a Linux distribution to provide self-hosted turnkey solution for schools. We use only Libre licenses and provide some advice to other teams. In 2016, we presented our OpenNebula use cases in our first participation to the OpenNebula conferences. Today, I will only highlight few points from that talk to explain what changed since that time. The first talk on slide can be found online. Last time, I described our storage area network accessed by the shared disk file system GFS2 with the required chorusing, pacemaker, and cluster LVM stack. Unfortunately, we never managed to make it reliable. When it was working, it worked fine. But when something happened, everything was crashed and required a complete reboot of the cluster to return to a stable state and resume the service. The second problem was the conception of SAN and GFS2 themselves. There was no balancing between LAN, making some LAN in use in practice, and concentrate the I/O on a single one. Preparing this year's OpenNebula talk, we realized that we built our first OpenNebula infrastructure 10 years ago, and we are now at the third cluster. We started with the testing but in production 2 powerful workstation, and the previous one was a SAN attached one. At the time of preparing these slides, we reached 800,000 virtual machines cumulated, at a rate around 1,000 virtual machines per day between the Jenkins CI and the developers' environments. This last cluster is composed of 6 machines, one for the OpenNebula frontend and SoulStack server, and 5 as hyperconverged hypervisor and SoulStack agent, running LizardFS, providing the cluster storage. The storage is composed of 10 SSD per server and uses a dedicated dual 10 GB networks interface. It exposes 36 TB of raw storage for data store, and today we reach 51 TB of QCoder images using 27 TB of storage. The main advantage with LizardFS we saw when looking for hyperconverged infrastructure was the memory footprint. The metadata server consumes less than 1 GB of RAM, and the chunk server storing the parts of QCO files only 100 MB. All the QCoder files chunks are equally balanced on each hypervisor automatically. The balancing is redone when a chunk server is removed or added, and we already tested it in production, and the recovery was flawless without much effort, not like our previous GFS2 stack. The virtual machine moved, the machine was stopped, and after the required hardware change, it came back online and the rebalancing started. Sadly, the future of LizardFS is not shining. It's actually excluded from Debian since Bullseye because of the Python dependencies and build failures. It could have been manageable for us since we know Debian packaging, we could have contributed, but the upstream source does not look much alive and has too few contributors. It looks like it's time for us to look at the next move of the storage. Another change we did is that we started to publish our tooling used to operate on infrastructure. Note that as for useful links, we will see it at the end of the presentation. Unfortunately, we only publish a single tool to clean up old VM files in DOL state to avoid inode exhaustion of FileLib1 file system. The other tools are too tied to our setup to be published yet, and we lack time to generalize them. Other publishing we did was creating an appliance template based on the files found in the Kubernetes 1.21 service. The idea is to track most OpenNebula evolution in that repository for other appliances to be easily updated. The first appliance we built is a GitLab runner service providing Docker, Shell, and Packer workers. We started a K3s cluster appliance a little before the OpenNebula official one, which has the question of organizing an appliance community where we could contribute instead of duplicating work. We build our OpenNebula appliances using Packer in a GitLab runner virtual machine. The method has a drawback. It does not profit the storage copy on write facility when creating new images by this device. This could be solved by a Packer plugin, but again, we lack time to build one. Maybe the community has something to propose? The latest changes we did is to use Kubernetes. As we started to develop application for that target, we figured that developing using only Docker is not enough. The developer either run the application in dev mode on their workstation or inside the Docker using volumes. And when several components are required, they use Docker Compose, but it's far from the Kubernetes target. As a first approach, we built a K3D virtual machine to set up an all-in-one Kubernetes lab infrastructure. The target is for each developer to have its own Kubernetes infrastructure, easily started by an OpenNebula appliance, and deploy developer work automatically from the continuous integration. Several parts of the solution are yet to be defined to set up the continuous delivery of a complete infrastructure with the developed Helm. In parallel, we started to think on how to provide the new Kubernetes services to our users. For those who already have an OpenNebula, we plan to provide them our K3S service from our custom marketplace. And for people who want to self-host their service but are starting from scratch, one solution we plan is to distribute an OpenNebula to manage the lower layer. A lot of thinking is required before having the first spark, but things are going on. Thanks a lot to the OpenNebula team for the invitation. We appreciate all the work done. Thanks to all the Libre software community, it's a better world to live in with Libre software. And maybe see you next time.